All right, so this is going to be a video on polynomial division. It's kind of exactly what it sounds like. We're literally going to be dividing polynomials by other polynomials. What we're basically going to be doing here for the section objectives is we're going to find the zeros of a polynomial and determine their multiplicities. Okay, so multiplicities is probably a new word for you, but we're going to define that and make more sense of it as we go. The zeros of a polynomial can be thought of similar to the zeros of quadratic functions. A quadratic function is a polynomial itself as well, so you'll see a lot of carryover from that last video. Next, we're going to be carrying out polynomial long division and synthetic division. And lastly, we're going to apply the remainder and factor theorems while we're actually doing this polynomial division. All right, let's look at some more terms before we get to some examples. Polynomials, an nth degree polynomial in the variable x has the following form. So if you notice right here, this is what a polynomial is. If you notice, it's very similar in structure to a quadratic because a quadratic is an example of a polynomial. Okay, the a sub n, a sub 1, a sub n minus 1, the a sub 0 are real or complex numbers with a sub n not equaling 0. So that first leading term cannot equal 0, similar to the quadratic formula, the a cannot be equal to 0. For this course, we'll mostly be interested in polynomials with real coefficients. In fact, that's what we're only going to be focusing on. Oh, it is important to note that all the exponents are just going to be integers, positive or 0. Okay, so integers that are positive or 0 is what the exponents are going to be each time. Right here, the zeros of a function are the values in which f of x is equal to 0. So that's exactly the same as the last video with the quadratics. A zero of a function is when the function is set equal to 0, and then you solve for those x values. And those x values are the x-intercepts, and those are basically going to be figuring out what the zeros are. Unless you have a complex zero. We're going to talk about that in a little bit. All right, to find the zero of a polynomial, you have to set the polynomial equal to 0. That's essentially what we're going to be doing throughout this entire unit, actually. We're going to be diving deeper into it with this video. All right, general polynomial equations are often solved by first making one side of the equation equal to 0. After doing so, the next steps may vary depending on the nature of the polynomial. For now, we'll focus on solving by factoring. Okay, so factoring polynomials and zeros. The thing that you have to understand for factoring polynomials is once you factor them, it's super easy to find the zeros. And I'm going to show you why in this example right here. So it says g of x is equal to this whole thing right here. This first zero they're talking about here, x equals 1, if you notice right here, it says x minus 1. Okay, that x minus 1, if you solve x minus 1 equal to 0, you would get x equals 1. It's almost like the sign basically shifted. It was a negative here. You can see it says x minus 1, and then it becomes positive over here. That's not really why. It's because you just set it equal to 0 and solve, and it flips the sign, but you kind of use that as a rule of thumb. The next one, x plus 5, x minus 5 is the next zero. And then lastly, x plus 8, if you notice it's x minus 8 over here. And their multiplicities is based on whatever the power in factored form is. So if you notice right here, this x minus 1 has a third degree right there. It's third power. The multiplicity, therefore, is 3 for this. So you can even write it as x equals 1 multiplicity 3. You can use like a lowercase m there. The next one, the negative 5, has no power there, so it's just an invisible 1. So it's basically x equals negative 5 multiplicity 1. Okay, and the next one is right here, it's a 2. So it's going to be x equals negative 8 multiplicity 2. So multiplicities basically are just stating how many times does that factor show up? What is the power wherever that 0 is when it's in factored form? So if you notice the 3, the 1, and the 2 are just the exponents for factored form of the equation. The next thing is an actual example where it says find the zeros and their multiplicity. So we're going to do that now. First thing that I would want you to find is the 0 here, which is just going to be x equals 0. Okay, it's just by itself. You don't have to really do much math with that. The next one, x minus 1, well, just set that equal to 0 and solve. Okay, add 1 to both sides. Now you get x equals 1. And the last one, x plus 2, set that equal to 0. Subtract 2 on both sides, you get x equals negative 2. Now there's the zeros for each of those. Just set all the factors equal to 0 and solve. The multiplicities are whatever power comes along with it. So this first one is 0. It has a 7 for the power, so it's multiplicity 7. The next one, it's 5, so it's multiplicity 5. The next one, it's invisible. It's just a 1, so you're going to say multiplicity 1. And basically, that's the answers for this problem. This one, that one, and this one. Okay. So that's how to figure out the zeros and multiplicities from a factored form of a polynomial. Now, sometimes it's not in factored form, so that's essentially what we're going to be doing in this video, and the next is dealing with it when it's not in factored form like that. All right, this next section is about polynomial division. As long as you don't try to divide by 0, any two whole numbers can be divided to obtain a quotient and a remainder. For example, 26 divided by 3 is equal to 8 remainder 2. Now, where does this 8 remainder 2 come from? Hopefully this kind of rings a bell from elementary school because it's essentially what this section is going to be about. So 26 divided by 3, if you remember from elementary school, you can write it as 26 like this, divided by 3. Now from here, you have to look at the leading terms. So we're looking at the 3 and the 2 initially. And you have to think, what can you multiply 3 by to get 2? Without going over. Well, the problem is 3 is bigger than 2, so you cannot multiply up any whole number without going over. Even if you multiplied it by 1, 3 is going over that 2. So if you want, what some teachers did in an elementary school is you can just put a 0 here. And there's nothing that you can actually do there, but we're just going to kind of leave it blank because we don't need to worry about that. So now we have to look at the 26 as a whole. What can you multiply 3 by to get 26 or something close to 26 without going over? Well, that would be 8. So now you would multiply this 8 by this 3 to get 24. and then you subtract. Because 8 are accounted for, 8 of the 3's are accounted for, so we need to subtract off that 24, and you'll get whatever you have left. In this case, the remainder. So 26 minus 24 is 2, and you're going to get 8, remainder 2. Another way of thinking about this is if you did 26 divided by 3 as a fraction, so let's just say we did 26 divided by 3 as a fraction, you can make this a mixed number by thinking, okay, there's 8 of them. Okay, now with the 8 times the 3 is 24, there's 2 left over, so you end up with 8 2/3. In fact, if you did 26 divided by 3 in your calculator, you would get 8 2/3. You know, if you use a decimal calculator, you get 8.6 repeating, which is the same thing as 8 2/3. That 2 at the top there represents that remainder. Okay, that remainder of 2. Now we're going to be using the remainder in a different way because we're going to be using this with polynomials, but the entire idea of quotients and remainders still holds true. So you have to understand that elementary school long division to be able to do this long division that we're going to do right now. Okay, I'm going to skip these notes for now. We can kind of go over them in class later because I would rather just do this by an example. Okay, this is not one of those things that you can kind of just learn by looking at it. We got to have to do some examples to really make it sink in. So it says right here, use long division to divide 3x squared plus 3x minus 14, and then we're dividing that by the x minus 2. So first thing that we're going to do is we're going to set up the problem. Just like we did 26 divided by 3, we're going to write 3x squared plus 3x minus 14, and we're going to divide all this by x minus 2. Okay, just like we had the 26 divided by 3, now we're doing that polynomial on the top, that quadratic, divided by the x minus 2. Just like before, we're going to look at the leading terms. We're going to look at x and 3x squared. So now you have to think, what do you multiply x by to get 3x squared without going over it? And the answer would be 3x. So if you multiply 3x by x, you are going to get 3x squared, which is awesome because we want to cancel that out. And then we're going to multiply the 3x by this negative 2 here, and you're going to get negative 2 times 3x is negative 6x. We're going to put this in parentheses because we're going to be subtracting, and you want to make sure you distribute what you're subtracting. Then from here, we're going to cancel. The negative and negative become a positive, and now you have 9x minus 14. Now we have to repeat the process again. What do you multiply that x to get 9x? And it would be 9. So we're going to do plus 9 here. Again, you do this waterfall thing where you multiply it by both of these here, and you're going to get 9x minus 18, parentheses again, subtract. If you notice, that leading term now is going to cancel. This flips the sign here, and you end up with a remainder of 4. So the answer for this one would be 3x plus 9, remainder 4. Or another way of writing it is 3x plus 9 plus 4 over whatever you're dividing by, which in this case is x minus 2. I would write both of them for this one. It doesn't actually say which it prefers, but just make sure whatever the problem asks for, you answer it that way. So if it's in remainder form or just fully simplified. And hopefully that makes sense. We'll do some more examples. All right, for this one, use long division to divide. So it's the same kind of thing that we just did. So we're going to write 6x to the third minus 5x squared minus 3. We're going to divide this by 3x plus 2. Okay, the leading term is 3x and 6x cubed, so you have to multiply that by 2x squared to get that 6x cubed, and now we're going to get 6x cubed plus 4x squared. Parentheses, we're going to subtract that off. From here, we're going to cancel here. This negative is going to go over here, and you're going to get negative 5x squared minus 4x squared, which is negative 9x squared minus 3. Then from here, you have to think, what do you multiply 3x by to get the negative 9x squared? And the answer for that one is going to be negative 3x. So you'll have negative 9x squared here, minus 6x, parentheses, subtract. Hopefully you notice the way of doing this is very similar. It's very methodical. You just have to kind of repeat a bunch of stuff. This and this are going to cancel. Switch the sign here, and you're going to get 6x minus 3. Repeat the process again. It's going to be a plus 2. So you're going to get a 6x plus 4, parentheses, subtract, cancel, and you're going to have negative 7 for the remainder here. So remainder, negative 7. Now the fully simplified way of writing this would be 2x squared minus 3x plus 2 minus 7 over 3x plus 2. And that's the final answer for this one. The remainder is negative 7, but if you had to write it as a fraction at the end, it would be negative 7 over 3x plus 2. Now, an important thing to understand on this is if you multiply this huge thing right here by 3x plus 2, you would get this original part right here. So we divided it. If we multiplied it by 3x plus 2, you would get where you started. We're not going to do that on this video because it's just going to take a lot of time up, but just thought I'd say that right now. Okay, very important idea. When the polynomial p of x is divided by x minus k, the remainder is the value of p of k. This idea is called remainder theorem, and you definitely have to understand this term and when to use it, because it's going to specifically say sometimes, using remainder theorem, figure out what the remainder is. And the way that you can do that is just dividing it. So we're going to look at an example here to just kind of make sure this makes a little bit more sense. So it says right here, let f of x be equal to 2x squared plus 3x plus 1. Use division to compute f of 2. Now, just for fun, I'm actually going to plug in and just find f of 2 right now. And you're going to notice at the very end, you're going to get the same exact thing. So you should get 15 for this. So our final answer, we should have 15. When we use the long division, we should get 15. So let's do that. We're going to have 2x squared plus 3x plus 1, and we're going to divide it by x minus 2. Now it says x minus k, p of k. So what we're going to do, it's f of 2. So we're just going to do x minus 2 because k is equal to 2 there. If you're wondering why that x minus 2 shows up. I'm just using the remainder theorem, the thing that it says at the top. So first thing is we're going to multiply this by 2x because 2x times x is 2x squared minus 4x, parentheses. Okay, the 2x squared is going to cancel. Negative, negative becomes a positive. You end up with 7x plus 1. Okay, that means there's going to have a 7 up here. And you'll have 7x minus 14 here. Subtract that off, cancel, cancel, flip the sign here, and you end up with 15 as the remainder. So therefore, the final answer is 15 because of that f of 2. So essentially, 15 is the answer, and that's how you solve it. Now, again, you could just figure it out by plugging in the 2, but it says specifically you have to use division. So if this was on a test, I would look specifically for, was division used, or did they just plug it into the original equation? The main thing is doing that long division, because that's what it says to do. All right, you're probably noticing that long division is very long and arduous process. Well, synthetic division, luckily, is a way of streamlining this whole process and making it very efficient. So synthetic division only works when you're dividing by something that looks like this, so x minus k. So there's no number in front of the x, it's just an invisible 1, and you're subtracting some value k from it. So it'll actually work for this one right here. But if we were using some other, like say we're dividing something by something else, let's just say we're dividing by like x squared plus 2 here, you could not use synthetic division on this. Okay, because it's x squared. It has to be x minus k, otherwise you can't use synthetic division. But thankfully, a lot of the problems do show up like that, so it's kind of easy to figure that out. So synthetic division is another process that you have to kind of memorize your way through, and the easiest way to learn this, in my opinion, is just by doing example problems. So that's what we're going to do right now. So it says you use synthetic division to divide this. Now, first thing that we're going to do is we're going to set up the synthetic division. What you have to do is you have to put the root of whatever you're dividing by. In this case, it's going to be negative 2. I'm going to put that on the outside here with like a backwards L as kind of like a barrier from it. So negative 2, and then there's like a backwards L there. The next step you're going to do is use all the coefficients from the polynomial that's going to be at the top, the numerator of what you're dividing by. So in this case, I'm going to put a 1 here, then a 3 because there's a 3 there, a negative 4 because there's a negative 4 there, and a negative 12 because there's a negative 12 there. And if you notice, it has to go down in order. So the first thing is x cubed. First thing is x cubed. The next thing is x squared. The next thing is x to the first. The next thing is x to the 0. It has to go in order. If you're missing one of those, you have to put a 0 as a filler there. You'll be seeing some example problems where there's a 0 in there. So this makes a little bit more sense. So that's first is just setting it up like this. You put the root on the left with the backwards L, and then you put all the coefficients down, and then you put a little line there. The next step is you put an arrow down like this, and you drop the 1. Then you multiply this by this, and you get negative 2. Then you add downward. So now it's going to be 1. Then you multiply this by that, and you get negative 2 again. You add downward. You're going to get negative 6. Then you multiply again by negative 2, and you get 12. You add downward, and 0. That last column there, that 0, is going to be the remainder. There is no remainder for this, so then whatever you have left is the answer. But we have a 1, a 1, and a negative 6. It doesn't help us much. Well, you had an x to the third, and you got rid of one of the x's by dividing it. So this x to the third now becomes x squared. So that first one is 1x squared plus 1x plus negative 6. So that would be the answer for this whole thing. Obviously, you have to simplify it, and it would just be x squared plus x minus 6, and that's the final answer for this problem. Okay, you have an x to the third plus a bunch of other stuff, and when you divide one of the x's by it, you lose a power. So it went from x to the third to x squared, and that is the answer for the synthetic division example. The next one, it says, let g of x equal x cubed minus 5x plus 7. Use synthetic division in the remainder theorem to compute g of negative 3. So what we're going to do is use synthetic division. Again, we can just plug that negative 3 in, but it says use synthetic division. So I'm going to plug the negative 3 in for synthetic division. That's the root, negative 3. Okay, and then we're going to put a 1 here. There is no squared, so I'm just going to put a 0 in for the x squared, a negative 5 for the x, and then a 7 that's just sitting by itself. And then we're going to put a line here. You always drop down that first term as a 1. Then you multiply to get negative 3. So multiply 3 by negative 1, you get negative 3. Add downward, do the same thing again, multiply here, you get 9, add downward, then you do the same thing again, you multiply over here, and you get negative 12, and you end up with a remainder of negative 5. Now it says using remainder theorem, figure out what g of negative 3 is. Well, g of negative 3 is equal to whatever the remainder is. Well, the remainder is negative 5. So the answer for this one is just going to be negative 5. Another way of doing that is if you just plugged in negative 3 to the original equation, but again, it says you cannot do it that way. You have to use synthetic and remainder theorem. But let's just say we want to check our work and do it that way. So it's going to get negative 27 plus 15 plus 7. Okay, well, this is 22. 22 plus negative 27 is negative 5. So it does check out. That is our answer for this problem. And we did it correctly. We used synthetic division and remainder theorem. Okay, very important idea. Factor theorem. X minus k is a factor of the polynomial p of x if and only if k is a 0 of p of x. So if you plug in, say k is 1 and you plug that into the polynomial, you will get if you get a 0, that means that x minus 1 is a factor. So it's similar to remainder theorem, only it's remainder theorem if the remainder is 0. If the remainder is 0, then it's a factor. So that's what we're kind of use that idea for this problem. So it says right here, if a polynomial has zeros at x equals 0, x equals 3, and x equals negative 1, then the factors have to be x minus 3, and x plus 1. Because it's always x minus the roots. So x minus 0 is this one, x minus 3 is this one, x plus 1, because it's really minus a negative 1, is that last one. So basically, if it's a factor, it's not going to have any remainder. That's the moral of the story for that. So right here it says, determine if x minus 1 is a factor of this. So all we really need to do is figure out what is f of 1. Okay, if f of 1 is equal to 0, then yes, x minus 1 is a factor. But if f of 1 is not equal to 0, then no, x minus 1 is not a factor. So we need to figure out what this value is right now. So we're going to figure out what f of 1 is. F of 1 is equal to 7 plus 4 minus 9 minus 1 minus 1. All right, well, this is 11. Okay, 11 minus 9 is 2. 2 minus 1 minus 1 is equal to 0. So the answer then is this part right here. Okay, f of 1 is equal to 0, so yes, it is a factor, and this one can basically be ignored because it is equal to 0. But if it wasn't equal to 0, it would not be a factor. So that's a video on polynomial division. We also covered other things like remainder theorem and factor theorem. This is a lot, but make sure you take good notes. Make sure you do the homework problems as well, because it's going to really seal this in, but you're going to have to practice this a lot because it's techniques that you kind of have to memorize on how to do them. So if you have any questions about anything in this video, let me know.